On Friday, we talked a little bit about single replacement reactions. So we'd start with this for, if we had this, we'd start with magnesium here, right? Magnesium's a solid, it's an element, right? So we're going to make sure we put the state down there with that. Sodium chloride. Sodium chloride would have to be in a solution, and I think we talked about kind of why that is. Well, we kind of talked a little bit about it, I think, on Friday with one of the ones I gave you. Maybe I'll just mention it again here today, but we would put that ionic compound as a solid. Look, if you took a solid and a solid and you reacted the two together, probably not much would happen because two solids mixed together, but that's probably what we'd end up with. So we need to have one in a water solution, so that ionic compound has to be in a water solution for this to happen. That's going to be the case with single replacement reactions. Yep.
On Friday, you said there's you're going to explain why.
Okay, I'll do that. Remember, this is the metal, so it switches with the metal, yes? So those two will switch places. We talked about that on Friday. We said they don't really like switch, right? It's just the transfer of electrons from one metal to another. So we're going to get sodium by itself, which would be the solid now, and magnesium chloride. 2 plus 2 minus, or sorry, 2 plus 1 minus, yes? Okay, so we still need to use those charges. We still need to balance it, of course. So what do we got here? 1 Na, Na, Mg, Mg. I think I need a 2 there and a 2 there, if I'm not mistaken. Okay? Good? All right. Yeah. Yeah, absolutely. Ionic compound, so swap them around. Remember, this was a zero charge. We talked about this on Friday, right? It's an element by itself, so there's no charge with that. This has got zero charge as well. That's a neutral atom, okay? This is where the charges come in because, of course, it's an ionic compound. So ionic compounds are made up of giving and taking electrons. Sodium loses an electron, chlorine gains that one. 1 plus 1 minus, swap, drop, and reduce, and equals out to 0, yes? So remember, we talked about how does this one, this is a 2 plus and that's a 1 minus, yes? So how does this magnesium become magnesium 2 plus? We would say what? It loses 2 electrons, yes? Okay, is what we said on the other day here. Loses 2 electrons. This one here, okay, each sodium, if you just look at the sodium, sodium's a 1 plus to a 0, that's gaining 1 electron. So this gains 1 electron, and there's 2 of them. So it gains 2. And so again, basically what's happening is, in this case, magnesium's losing those electrons, and sodium is gaining those electrons. That's what's happening here, okay? Chlorine, or the chloride ion, there's something called the spectator ion. We don't need to worry about that. But basically what's happening here, and again, the reason we need to put this into water is because if we don't put it into water, if we just had a solid here and a solid here, that would just, can you imagine just taking 2 solids and dumping them into a beaker and saying, okay, let's watch what happens? Nothing, probably, yes? So nothing's probably going to happen. I mean, I guess you could add some heat to it or something like that, but that's not really what this reaction is all about. This is our single replacement reaction, so the ionic compound should be aqueous. The reason it needs to be aqueous is because when we put sodium chloride into water, what happens to sodium chloride when you put it into water? Yeah. Yeah, it splits apart the compound, yes? And when it splits apart the compound, now I have sodium ions and chloride ions, okay? So when the water splits that apart, now there can be that exchange between these two here of electrons, okay? That's basically a single replacement reaction, all right? Without water, it would stay together as a compound and nothing would happen because there's not that medium for there to be an exchange of electrons, okay? So we need the water there to make that happen. Single replacement reactions will always be something plus aqueous ionic compound, okay? Always aqueous ionic compound in this case. So here's where it gets a little tricky. When we talk about ionic compounds, we always talk about solid form at room temperature, and that's true. If you're trying to form an ionic compound, it's a solid. If you're trying to decompose an ionic compound, it's a solid. Combustion reactions, well, that's usually like a hydrocarbon for us, like carbons and hydrogens, so we don't talk about that. But then for a single replacement reaction, it's going to be aqueous, because now we need to put it into water, and we're going to get an aqueous thing there as well. Okay, and we'll talk about double replacement coming up here. All right, let's move on here. Type 2, did we? I don't think we did type 2 yet, have we, on the thing? Okay, well, let's do this. I think what they want you to write in there, if I'm not mistaken, is, where do I put my sheet here? Right here. So for type 2, it says a non-metal reacts with an ionic compound. So let's call it, I don't know, I think they use Y plus AX. So this right here is your non-metal. So if you get a non-metal that reacts with an ionic compound, okay, you're going to get a switch of the non-metals. So we'd get X and AY, okay? So again, when you talk about ionic compounds, there's two different types, okay? This right here is what determines what type of ionic or what type of single replacement reaction we're going to have. If this is a metal, okay, listen closely. If this is a metal, this was last day. Metal switches with the metal, yes? If the non-metal, it switches with the non-metal, okay? So whatever this is kind of tells you that, okay? Like I said, if it's a metal, it switches with the metal. Non-metal switches with the non-metal. They give you an example there, and then the second one says, write the balanced chemical equation for the reaction that occurs when liquid bromine, okay? Bromine, don't forget, is one of those molecular elements, Br2. I have no bright or clever friends, people stupid. Is added to a solution of iron 3 iodide. Solution, okay? Iron's a 3+, iodide's a 1-. Okay, we're talking about ionic compounds, so we got to use the charges. So when this takes place, again, non-metal switches with the non-metal. Now, these are like probably not quite as common, these ones are, but nonetheless, we need to basically take the non-metal and switch it with the non-metal. So the iodine has to come out. When iodine is by itself, it is I2, H2, N2, O2, etc., F2, E4, S8, things like that. Iodine is a solid at room temperature. Okay, so we're going to put that down. And then the bromine is going to go be part of the iron 3. So iron 3 bromide, like so. All right. Iron's a 3+, bromide is a 1-. That bromine becomes a 1-. Okay. These are what we call molecular elements. So you might say, well, why is there Br2 and I2? They're across the top there on your periodic table. I have no bright or clever friends, people stupid, or a Hofbrinkel. Okay. The other ones are part of the ionic compound. So we use the charges from the ionic compound. Iron's a 3+, I is a 1-. Iron's a 3+, Br is a 1-. So we swap and drop. Balancing, we're going to have to do a lot of switcheroos here probably because that's 3, well, whatever. 2 here, 3 there. So I'd probably put a 3 there and a 2 there, like so. 2 FEs there, 2 FEs there, 6 and 6. Something like that there. Okay. Again, these aren't very common, but it can happen, of course. These ones are a little tricky, like I said, because the non-metals, a lot of the non-metals, of course, are those molecular elements, which are Hofbrinkel, I have no bright or clever friends, right? Kind of stuff, okay? So, moving on here, we're going to talk about double replacement reactions. So, where's double? Let's see. I know, I think I skipped one there, it's fine. Double replacement, okay, let's talk about that. It says, in a double replacement reaction, the cations, okay, of 2 different ionic compounds switch places. Cations are, of course, the, where does it say it here? Well, the metal, positive ions, right? So the positive ions, I guess, just put that in there. Positive ions of 2 different ionic compounds switch places. Okay. The kind of the general idea of this is look kind of something like this here: AB and CD. Okay. Chances are this will be aqueous, aqueous. Okay. In this case, we're going to mix two solutions together now. Okay. Again, why are we doing that? Because we want to split AB apart into ions and CD apart into ions. Okay. And what usually happens is we say the positive ions switch places. So what we're going to do here, and there's only one type of double replacement, we're only going to switch the positive ions. All right. So those two there. So we're going to end up with CB and AD. Okay. I'll put here aqueous. Well, you know what? I'm not going to do that actually. I'm just going to put two things there, and I'm just going to leave them for now, I think. They both could be aqueous, okay, which is kind of a boring chemical reaction, and that usually happens when I screw up. Or usually what happens is one will be aqueous and one is going to be solid, okay? That's usually what happens, because when you take a double replacement reaction and mix them together, we quite often get something called a precipitate that's formed, and we're going to need your periodic tables out to decide that on the backside solubility chart. Okay, here we go. They give you an example there already with barium hydroxide and sodium sulfate, and you'll notice that the sodium and the barium switch places. Is that okay at the very bottom there? Okay. So I'm going to skip over that if that's okay. And that's actually, I believe, wrong. That bottom example there, by the way, what we're going to get our let's get our periodic tables out here. And let's flip them over to the back side. And actually, I'm going to bring it up here while we're doing that. So what we're going to be, obviously, okay. Obviously, what we're interested in there, just so you know, this is thinking here. Just wait. I guess I should probably. Oh, there we go. Oh. Okay, there we go. That's what we're interested in with double replacement. Okay. And if you look at this very bottom example here, I just want you to make a quick little note here. Let's look at the product side. And if I said barium sulfate, let's find that. Here's sulfate, yes, right there. So that's the sulfate. Remember, we did this before, right? This is solubility. Where's barium? Is it here in the most, or is it down here somewhere? Top or bottom here? Bottom, right here, yes. So that actually should be what? Solid. Okay, so let's fix that. Barium sulfate should be the solid there, yes? So it says aqueous, but let's put a solid there. Let's put an S there instead. Sodium hydroxide, by the way, just in comparison, here's hydroxide right here, and sodium would be a group 1 ion, so it would be very soluble aqueous, yes? Okay, so that one's okay. Like I said, usually what's going to happen here is we're going to get an aqueous, and we're going to get a solid, and you're going to have to use the chart to look that up. The notes are going to tell you that right away here. All right. Let's see here. Drop and swap. Don't forget the multivalent metals, so ones with more than one charge. Okay. Whatever charge you start with, that's the one we're going to end up with. Okay. So, for example, copper 1 is not the most common charge of copper, but if I start with copper 1, I end up with copper 1. Okay. So it's a little different than single replacement, because remember, single replacement, we use the most common one if we have to in an ionic compound. In this case here, we're going to start with whatever, and we're going to stick with that. Okay, whatever. If it's the most common or not, doesn't matter. Okay. Like I just said, copper 1 will give you copper 1. We'll see. You got to use solubility chart. One of the products should form a precipitate. That doesn't always happen. Okay, just so you know, but just keep that in mind. All right, let's get to the examples here. Where are we? Aqueous lead 2 nitrate. So again, quite often, if you know, most of these probably already give you the reactants, and sometimes they actually give you the products as well. Having said that, we should just be able to give you the reactants, and you should be able to figure out what the products are, okay? So aqueous lead 2 nitrate, let's start with that. I'll do the first one here, aqueous lead 2 nitrate, and aqueous sodium iodide. Okay. Now, I quite often run out of room here, so just bear with me. I'm going to write it on the next line. Double replacement reaction. How do I know? Well, ionic compound plus ionic compound. And if you remember, we talked about how do you balance an ionic compound? With an ionic compound, it gives you ionic compound. We balance it based on ions, yes? So I would probably say, okay, well, first of all, I guess I need to write out the equation here. Now, whether it tells you this or not, I don't know. Does this one tell you what the products are? No. Perfect. Okay. We know that I need to switch the metal and the metal, yes? Okay. So those are the two that I'm switching. So I'm going to put sodium with nitrate. So I'm going to write that maybe here. And what you should get in the habit of doing is putting that there, because you got to know that you got to come back and fill that in. And then the lead 2 goes with the I, right? Lead 2. So 2 plus 1 minus, and swap and drop. And again, I'm going to have to put something into there. Okay. So when we get to these double replacement ones, again, one mark is always going to be for the states, one's for the skeleton kind of equation, one's for the balancing. So you can't forget about to fill in the states here kind of thing. You're going to look these up, of course. Okay. And it's kind of up to you which one you want to start with, to be honest. Sometimes you'll kind of figure out over time here that, you know, after you use this enough times, which you will, you're going to find that sometimes it's easier to find one than the other one, but it doesn't matter for right now. Here's I minus right here, right? And I'm looking for lead 2. So right there, yeah? So lead 2 and iodide should be the solid, right? Okay, so right here, we're going to go solid. And then I'm going to tell you right now, you probably don't need to look the other one up. If you want to double check it, you can, but this is going to be aqueous here. Aqueous there. And we can double check it. Here's a nitrate right here, NO3 minus. Most of the ions are sodium, right? Right there. I don't see it anywhere there, so I think we're okay. Okay. Balancing now. So quite a lot to do with this one. You got to obviously predict products and then balance it. Lead here, so we're good there. 2 NO3s, right? 2 NO3s, 2 nitrates. So I'm going to put a 2 there for the nitrates. Yes. 2 NAs. Better put a 2 there. 2 NAs. 2 I's. 2 I's. So we should be good. Okay. We've got a balance based on ions there. That's pretty important. Okay. Questions, anyone? Yes, no? Well, positive ions compared to lead 2, yes. Balance based on the leads. Nitrate, we're not going to balance each element by itself. We're balancing it based on the entire thing, nitrate. Okay. The next one is, what is it? Solution of, I'm going to let you guys go ahead and start. Go ahead and start. Copper 2 bromide and aluminum chloride. Let's see how we do here. All right, so this is where we'd start, of course, yes. Copper 2 bromide, so copper is a 2 plus, bromide's a 1 minus. Aluminum is a 3 plus, chloride's a 1 minus. We switch the metals, so copper and aluminum will switch places. We're going to get some AlBr, and again, 3 plus aluminum. Br is a 1 minus, so swap and drop. I probably should put a little thing like that there because I'm not sure what states we're going to end up with there. And then copper 2, remember, and chloride, right? Copper 2 and chloride, 2 plus 1 minus, swap and drop, okay? And let's not forget, we got to fill in the states, okay? So aluminum bromide, first of all, here's Br minus right here, and aqueous probably, yes, I would think, correct? Okay, so most probably right here, yeah? Al3 plus and Br minus, because I don't see it down here, so let's put aqueous. Okay. Copper 2 chloride. So here's chloride, right? And copper 2 here. Here, yes. That was a quiz question, remember? Also, aqueous, right? So, oopsies, aqueous. So we don't have a solid in this case, all right? And that's okay. All right, so you have to be aware that sometimes they don't always produce precipitates. To be honest, if you mix these two together, I can show you when we go to the lab here one of these days. We're going to have one more little lab thing here coming up, but when we go to lab, if you mix these two solutions together, you basically would see nothing happen, okay? And I'll explain why that is, I think, here, if I have enough time, okay? But balancing-wise, let's see here. Copper is good. Br2, Br3. So again, looks like I'm going to have to probably do a little bit of that. 3 coppers, 6 chlorines, 2 aluminums, 2 aluminums. Probably a little something like that there. Okay, that's usually what happens when you get that 2-3 thing there. You're going to be doing 2s and 3s kind of to balance that out to make 6s. Okay, so that one's kind of a boring one. That one doesn't. That reaction probably wouldn't be too exciting to see. All right. Good? Yeah. Yeah. Yeah, you just keep with the copper 2. Yeah. Okay, last one here. You guys go ahead and start that one. It is the well, don't worry about the word equation. Silver nitrate and potassium phosphate are mixed together. Solutions of both of those. All right, so we're going to start with 2 solutions. One silver nitrate, the other one's potassium phosphate. Silver's a 1 plus, nitrate's a 1 minus, of course, so we get that formula there. K is a 1 plus, phosphate is a 3 minus, polyatomic ion, that's right, swap and drop. And again, we're going to switch metals. So I'm going to put the K, and by the way, it doesn't matter which way you do this. It doesn't matter which one you write first. K and NO3 I'm going to put together. So that's potassium nitrate. That's a 1 plus and a 1 minus. And I'll just leave that there. And then I'm going to put silver and PO4 together. Silver is a 1 plus. PO4 is a 3 minus. So I'm going to put that there, right? Swap and drop. 1 goes over and down. I don't write it. 3 comes over, etc. I'm going to have to look up the states. This one I know is aqueous. To be honest, I don't remember that one, so I guess I'll look it up, but I'm pretty sure it's the solid in this case. Here's PO4 right here, okay? And then we got to find Ag1 plus. So is Ag1 plus here? No. Okay, it's right here, yes. Ag1 plus is not a group 1 ion, and it's not NH4, so Ag1 plus is, I don't know, somewhere in the middle there. So transition metal there, okay? So I know that that's the solid here, and I'm going to put solid, okay? So let's not forget to do that, of course, because that's part of your marks there for that. Well, I'd probably start here. I don't know, we'll see, I guess, what happens, but Ag, Ag3, yes? So I'm going to put a 3 there. That means that's good, and that's good. I got 3 NO3s, 3 NO3s, right, nitrates, 3 Ks, 3 Ks, probably PO4, and PO4 is going to be good then, because that's the last one. I mean, if the PO4 and the PO4 didn't match up at that point, if that's your last one, yeah, that's probably not going to be good. It should by that point, because everything else is balanced, right? So those two should probably match up. Okay, good. Any questions, anyone? I know that was kind of fast today, but I want to give you a little bit of time to do some stuff here. But any questions, anyone? Yep. Yeah. Well, the metals have to be the first ones. Yeah. They have to be, because it's ionic compound, so the metals have to come first. Yeah. Yeah. You could switch the anions, but you're basically doing the same as the cations. In all honesty, it's not. I mean, if you really want the technical definition here, what happens is, you know, when you take an ionic compound and you put it into water, what happens? Well, you get I'm just gonna pick some ions. That's not the point here. And B minus, yes. Okay, whatever those are, aqueous. Water breaks them apart, yes. And then here you get some C and D, yeah, in that beaker there. So you're taking, like, for example, sodium, well, in this one, silver nitrate. Don't worry about the charges or anything. You get some silver nitrate here, and you got some potassium phosphate here, yes, in these two beakers. And when you mix them together into one big beaker, here's what happens, okay? You get A, B, C, and D all together, okay? So it's not that the metals, like, again, we say the metals switch places, okay? But they're not switching places, right? What's happening here is, remember, ionic compounds is all based on what? Charges. What about specifically charges? No, not necessarily. Well, yes, between A and B and C and D, but what's ionic, in the big scheme of things, what are ionic compounds made up of? Or how do they bond together? They bond together based on, yeah, which is more specifically, huh? Yeah, opposites attract, yes. So when you get all these ions into one beaker, look what happens here. Is A attracted to B? Is A attracted to B? Are these two opposites? Are they attracted to each other? Okay, they are. But we already said, look what happens when A and B is in water. This is all in water here, right? So we put this in water, and this is in water. I'll make it better for you. It's blue. There you go, okay? And then this is all going to be in water, yes? Okay. What happens when A and B are together? They come together, and then water does what? Breaks them apart, right? We already did that. So A is attracted to B, but they can't stick together because water breaks them apart. And C is attracted to D, but water breaks them apart, yes? So then what's left? Well, there's opposites are still attracted. So is C attracted to B here in this case? Yeah. Okay. And is A attracted to D? Yes. But once again, I don't remember which one is which now, but C is, I'll just say, for example, C is attracted to B, but water splits it apart. Yes? So that's how we write that. So we're saying, hey, C is attracted to B still, but they're still split apart. And A is attracted to D. Well, they come together and they actually stay together to form the solid because water's not strong enough to split them apart. So that's where we get the precipitate from, okay? Good? Okay. So that's what's happening in a double replacement reaction. Now, not always does A and D make a solid, for example, or C and B for that. So in that case, we just get a bunch of ions that are floating around. You can't see ions in water, okay? I have to show you that, so I will do that one of these days here, probably tomorrow, hopefully, okay? But anyway, you got some questions at the bottom there, okay? And there's good, like I said, 1, 2, and 3, we're gonna have those done for tomorrow at the bottom there. There's good review here for all those. And we'll talk, we might have to, I don't know, we'll see here how tomorrow goes, but we might push here, I think we're supposed to have a quiz on Wednesday. We might push it back to Thursday just to make sure. Because we are done now, but maybe we'll give you an extra day here. But I'm looking at tomorrow, we might just give you some practice. We'll see. I'd like to move on because I don't want to get too far behind here, but we'll see how it goes, kind of thing. I don't need